Welcome to All the Best, an interview series with UNL ORCA awardees, where UNL means University of Nebraska-Lincoln, and ORCA is the Outstanding Research and Creativities Award, which is UNL's top award. In Gerda Lerner's book, Why History Matters, she explains the life stories give meaning to the present and the future because we identify what is important to us. And she says, our stories show how we are interconnected in a particular time and place. As for this interview series, ORCA awardees have experiences that reach back more than a half a century, which will give us a personal view of how the best research emerged from UNL. It is my pleasure to introduce today's interviewee, Professor David Hage. He was awarded the ORCA in 2018. After I provide a quick summary of his life and career, Dave will tell us about his time at UNL, starting with his award-winning research. Dave was born in La Crosse, Wisconsin, and earned his bachelor's degree in chemistry at the University of Wisconsin in La Crosse. Next, he earned a doctorate from Iowa State University and did postdoctoral work at the Mayo Clinic in Rochester, Minnesota. In 1989, he joined UNL as an assistant professor of chemistry and quickly rose through the ranks. He has won many awards, and for the past 13 years has been the James Hewet University Professor of Chemistry. Allow me to share some remarkable facts about Dave before we get to the interview. One is that his lab found a way to make very small chromatography columns that could withstand very high pressures, which allows rapid analysis of a wide range of molecules. Another fact is that he has published over 365 peer-reviewed publications, and that 10% of those papers have been cited more than 100 times. My third fact is that he has mentored over 77 graduate students who have received MS or PhD degrees, which places him among the most productive advisors in the department's history. Since more than half his graduate students have been women, it also means he has mentored more women than any other faculty member in my department. With that, I want to welcome Dave Hage to the interview.
Thank you for having me here.
Let's jump right in. What was your impression of UNL campus the first time you saw it compared to what it seems to you today?
The first time I saw it was in December of 1986.
Oh, wow.
I was there for my job interview, and I had a very positive impression. It was obviously a cold day. We had snow and everything, but it also turned out that that day there's a big faculty reception in the evening. So they took me to that as part of my interview. And one of the people there was actually the current governor, Kay Orr, who I got to meet and have a nice chat with. That was a lot of fun. That made a very positive impression. And one thing I really liked about her is that she was very pro-education. She started a lot of the initiatives on campus. She started the Center for Biotechnology, threw the money in for the nanomaterials work, Water Center. So it's a very growing area at that time. So that all attracted me here. And there's also a real area of growth that I saw for maybe coming into a chemistry department that wanted to go a lot more into the biological chemistry area. They kind of started that, but they were moving a lot more in that direction with the chair that they had at that time, who was a biochemist. So it was a very positive impression that way. In terms of how it compares to now, I mean, it's grown a lot since then. All those things that started then are now actually pretty huge facilities.
They are.
Really grown a lot. There's a lot more emphasis than there was back then on research grants. That grew a lot in the early 2000s. We had Prempal. It's always been pretty tight on campus. I was like that when I came in to visit, and I still think that's present here too. Another thing I was warned about when I first interviewed here was a big football campus, and that hasn't changed at all, except they lose a little bit more now than they did. But no, that didn't make any difference to my interviewing though. But I knew it was kind of a medium-sized sound. That's what I was looking for. Someplace I could do research, but not so big that, kind of get lost in the weeds. So like a lot of things the same, but it has actually grown a lot in terms of research on this campus over the years.
Great. Now let's jump into your award-winning research. Give us a sense of how it came about and what it actually is and why is it important?
Okay. Well, my general area of research for which I won the award is in affinity-based separations and analysis methods, which I'm an expert in and probably one of the world experts, actually. And I got into that going way back to when I was doing my undergraduate work. I was interested in chemistry and biology both, and we'll get to this later on. But I wanted to combine the two together. And in my graduate work, I found that maybe I could do that by taking this relatively new area of high performance liquid chromatography and combining that with biologically recognition type events like antibiotigens, stuff like that.
And this was Iowa State.
Yes, this Iowa State there, yeah. And so then I continued doing that a bit in my postdoc, learning some new directions, and I came here with an emphasis on that. I didn't see a lot of the people working in it, and it seemed like a challenging enough area that I could make a big impact without having a lot of competition, at least for a few years. Gets a lot of funding, had some novel ideas. And so that developed into lots and lots of areas that we're doing now still. I started out in developing ways of rapidly automating immunoassays, which has always been very important, like in biochemical and clinical analysis. So I did a lot of that initially. And then I also branched out pretty quickly into looking at things like drug and hormone transport in the body, developing models for biological systems, using separation devices. I unexpectedly went into environmental testing. I'll get into that a bit later too, but branched onto that, developing, since we're a chemistry department, using the methods we developed, developing new mobilization techniques, new supports, helping chemistry. So that all came about. So all that together, years and years of that is actually combined together to get the ORCA award.
Mm-hmm. So really, quantitation of things?
Quantitation, both measuring how much something is there and also studying the interactions of things together. So it's also a bit of physical chemistry from that aspect, biophysical chemistry.
And a very powerful technique. Tell us about one or two of your early graduate students or visiting scientists, and what were their projects and what happened in their careers.
All right. My very, very first student was Peggy Roon, who you know also.
I do.
She was actually here before I was. She joined a year before I did. So she was actually waiting for me to come. When she found they hired me, she was waiting to join a group. So I got her right away. I also had two other students that joined me right away as well, Dave Thomas and Boonton Loon. Peggy is still in the area. She worked originally at Bio Nebraska, a biotech company that was formed by faculty from UNL. And then she went over to Solarion, wasn't named Solarion then, was currently Solarion, worked for there many years. And now she's semi-retired, still doing work there, developing new projects, doing actually a lot of the stuff she started with me, developing things like standard operating procedures in the laboratory. She already carried that through a lot of her professional experience.
Absolutely.
So she's done well with that. Another person a little bit later is Annette Moser. She's probably 10 years later.
Yeah.
She came here. She's a Nebraska native. Wanted to do work in environmental testing, which I was doing at that time. Really, really wanted to go into academics and really, really wanted to teach at Kearney. So we kind of talked together when she first came. We worked out a plan where she could get educational experience, give her a lot of exposure to people at U and Kearney. And actually, she's the chair of the department there in chemistry. So it actually turned out well for her.
She's still the chair? She's been the chair for a long time.
She's been a couple of years at least. So yeah, so she got to meet her goal there.
Yeah.
And one more, Bill Clark. He's also late 90s, early 2000s or so, worked in my group. He was interested initially in going to academics, then changed to going to clinical chemistry when she saw some type of stuff we were doing. Did a postdoc in clinical chemistry after he got done here. And he's currently the director of clinical medicine at Johns Hopkins University Medical System. So he's done well also. Pretty big name in that field. So I'm pretty happy about all three of those.
Yeah. Okay. So we're both scientists. And so how does science define impact? How do you know when you've made it?
Yeah, well, a lot of people use impact factors. Impact factors are good, but they're not the only thing. So obviously number of citations, but I think seeing how much people use your work actually in their own research, if you see other papers, not just citing your work, but kind of developing the same area, that's good. I see development of graduate students as being important in science. I was trying to make that kind of a priority. It's like finding jobs and good fits for people that want to work in the field and training them for that. So again, it's not just about papers, it's actually the people too. I think actually people are more important in the long run, training the students and getting them out there into their field.
So I looked you up on Google Scholar. There's many ways that we could look up how many citations we have. And you have 3 publications with more than 400 citations.
Oh yeah, I do.
Which is remarkable, right? In my own experience, 50 or more is a very large number.
Oh yeah.
3 more than 400. So 2 of them are about affinity chromatography in the title. And then you've got glycation of human serum albumin, which seems like an actual research paper.
Oh, well, yeah, it is.
And that one, 486 citations. So why do you suppose that one is so popular?
Well, that one took me a while to actually get into that area. It was kind of a brainstorming thing I had. This was again like in the late 90s. I was trying to figure out a new direction to go in my research. And one thing I had been doing for a little while was studying bonding of drugs to transport proteins like albumin. And it occurred to me, okay, I have people on my wife's side of the family that have diabetes. I want to do something to help that group of people. And I noticed over the years that they often have a hard time regulating the medication. So I was thinking, okay, what could be the cause of that? Why they have such a hard time regulating medication? It occurred to me that a lot of these drugs bind to proteins like albumin, and glucose, which is albumin in diabetes, modifies proteins. So I thought maybe there's a connection there. So I came with this idea. I actually sent it out initially as a small grant to the Juvenile Diabetes Association to get funding. And now they're interested. They didn't go with it. Then I tried NIH. I said, okay, went to the study section. They thought it was kind of interesting, but at that time, there's very little data on this. There's people that looked at it a little bit, but there's very conflicting data. I said, okay, well, maybe. And then I do a revision on that and then finally got funding. And all of a sudden we found the problem was that people weren't using enough controls. They weren't doing the experiments under well-defined conditions, like they weren't controlling the level of glycation and so on. So we did all that. That was the first thing I looked at, make sure we can make this stuff reproducibly and at a level that's clinically relevant. So once we did that and we figured out a system using our chromatographic approaches to place the columns, and all of a sudden we could do all these studies getting very precise measurements of these drug and binding constants and how they were changing glycation, combine that with mass spectrometry, start looking at changes. We saw there's a correlation between where the protein is being modified and where the drug binding sites are, and we linked that also to the levels of glycation. So all of a sudden everybody's interested in it. And so then we came up with this paper kind of summarizing that result.
Wow.
And it keeps going up. That one getting a lot of citations. And we have a lot of smaller papers that are on this list further down that you're looking at, but combining onto that. But yeah, that one particular has been growing very quickly.
So that one cracked it all open. The key was measuring the level of glycation of the protein.
Controlling the level of glycation.
Controlling the level.
People were just mixing glucose and albumin together and not really. We looked at what's actually the body, the levels of albumin you normally have. We looked at the levels of glucose that might be present in diabetes. We mixed them together under as close as we get to physiological conditions. Use a time that mimicked the lifetime of albumin, try to get everything as close as we could. And then we did the experiments. Plus, we also isolated glycoalbumin from real samples and used that too. So that's what the big difference was.
No, fantastic. Then what was your most unexpected research finding?
Okay. Well, there's been a couple of them.
Yeah.
Actually, one early on, going back to this whole albumin thing, I kind of got into that by accident a little bit. So my very first student, Spoon Tan Loon, we were studying the transport and measuring thyroxine levels in the bloodstream. And thyroxine binds to lots of proteins. It has a major binding protein, thyroxine binding globulin, thyroxine binding prealbumin. Those are the big ones. And the albumin is kind of a smaller one. So we're trying to develop a model of describing all this. And initially, my student and I were going to mobilize thyroxine and see if these proteins bound to that. It worked out okay, but then my student said, well, we're getting a lot of non-specific binding here. It's hard to measure this. What if we change it around? What if we mobilize albumin instead of that and had thyroxine bind to it? I thought, well, yeah, then we have to worry about denaturing the protein and stuff. And then let's just try it. And it turned out to work great.
Wow.
We got the right All of a sudden, got lots of papers on albumin for all kinds of stuff. But basically figured out how to mobilize albumin in active form. And that really opened up lots and lots of opportunities. And other people have done the same thing. They've really lots of papers in that area now.
And it's not attached to one point, it's attached to multiple points.
Well, it turns out we did some studies on it later using mass spectrometry. There's many lysine residues on albumin, and our technique uses amine-based coupling chemistry. It turns out that the method that we found worked best, it's called the shift-based method, that uses a lower pH than most methods, it uses pH 6. So at that pH, the N-terminus is the one we're usually coupled through. So we lucked into it a little bit. But in hindsight, we can reason it out. But yeah, that was kind of the key.
So the key was attaching to one point that the drugs don't bind to.
As much as possible, yeah. But we proved it later on. That's what we were doing, but we didn't intend to do it then.
Sure. No, that was a good one. Do you recall papers that you thought were good or research directions that were good, but not among your most highly cited?
I think the work that we've done, at least the initial work that we did with environmental testing, using like antibody columns to capture triazine herbicides, different class herbicides, and doing multidimensional methods. It's gotten a bit of interest, but I think it could have been more highly cited. We are now doing kind of related things, but now instead of using antibodies, we're using natural dissolved organic matter, humic acids to capture drugs. So that's actually getting a lot of interest right now. So we use that as predicting transport and bioavailability of human-made substances, the environment, and we're getting a lot of interest in that work right now. So it does come around. I think that earlier work should have been cited more, but I did lead other people using immunofluorescence chromatography coupled with mass spectrometry. We often don't get credited for coming up with that idea first, but we did do it first.
Really? So, but humic acid probably has a huge literature. Maybe that's partly why
it is,
it's more acceptable.
People, obviously anybody working with soil science, environmental science, water, they all know about it. But no one's looked at it quite the way we have before. Great.
Tell me about, this is a big one, editorships, patent applications, companies, books, etc. We'll start with editorships. I know you got a lot.
Yeah, I've been editorial boards for several journals, but I've been an editor and editor-in-chief for Journal of Chromatography B for quite some time. And it's a bit of work. You do have to learn about time management for that, because I have to, obviously, you have to fit in with your other duties. You can't let it take too much time. But that's interesting. You get to learn to see like what people are doing in the field. You get a lot of input in terms of the quality of things that are published. And I'd like to think I'm fairly tough on that. Not letting things that aren't of good quality. There's actually quite a bit of stuff that goes in that doesn't go out.
Sure.
And seeing what people are interested in doing. Just give an opportunity also to review the area. So you've noticed one actually of my highly cited papers was developments of chromatography in the last 50 years. 280 citations. It's only been out about 5 years.
Oh, wow.
That one's going up fast.
That's hot. Yeah.
So that one, because I was an editor, I was able to get a pretty good idea of the field, kind of summarize trends and stuff, and that's got a lot of citations as a result. So that one has been going up very quickly, probably 50 citations per year.
Yeah, that's a lot.
Yeah.
So why should somebody be the editor? I mean, what do you gain by being editor-in-chief? Besides what you said, you've got input.
Well, I'm not in it for name recognition. I guess there is that. You get to work with other experts in the field and see where the field's going. The other people that are editors that I've been supervising and working with, they're from all over the world, people from China, various countries in Europe, sometimes South America, the United States, of course. So you get to see the different viewpoints. Like, for example, the people in Europe have very different viewpoints from the people in the US and from people from China in terms of separation of science. There's big areas of differences and emphasis there. So there's that, and then also contributing to meetings that way as an editor. I get to give workshops in terms of training people how to submit papers to scientific journals, how to work with the review process. I give the same kind of presentation to our new graduate students in one of our graduate programs. So
great.
Yeah. It's also a way of training people how to write papers. So I think that's been probably a very useful thing out of all of it.
No, that sounds really good. Patent applications.
Yeah, I have like 7, I think.
Yeah, where did I find you here? So your very first one, I think, was you got a couple from
Those were
2001.
about the same time, yeah.
Okay. Loading microcolumns for the separation of analytes from a sample in the, and I see.
Millisecond time domain, yeah. So there we were interested in seeing how far we could push down the size of columns that we use
Mm,
affinity ligands.
mm,
And it turns out if you look at the theory behind chromatography, with affinity ligands in particular, biological ligands, because of their tight binding selectivity, you can create very, very tiny devices with them. And it makes sense based on measurements we've made of their rate constants and equilibrium constants. It also makes sense if you think about where these agents are coming from. Biological systems, the bonding events are taking place usually in very short distances within cells, communication and stuff.
mm,
So they have to be fairly rapid to be able to communicate. And so we're just making use of that by using miniaturized devices. If you take, like, for example, an antibody, you place it in a microtidal oil plate or
yeah.
even on a bead, you're talking millimeters. You're not talking about the actual distance over which they normally exist in the body.
Mm,
So what we do is we actually, by using the small supports, we get to the same distance in the body. And that's how we can get to these rapid transports where it's a closer mimic to the actual biological system. Yeah.
Do you exclusively use the microcolumns, or do you have a whole range that you use
We use full
today?
range. We can make about any kind of HPLC column you want size, but we usually right now we tend to work. Well, I started out here working with things maybe 5 to 10 centimeters long.
Mhm.
Today, a big column for us is probably 2 centimeters. That patent that you're talking about there, we can make columns down to 60 microns.
Mm,
So basically the width of a human hair, roughly.
yeah. So what's the advantage? It's the time. It's the time. You need
The,
a
the
tight binder
type binder column residence time is
if you
very
want
short.
very short.
So it
Yeah.
allows us to explore some unique applications where you can have very short column residence times, like very high throughput analysis of drug protein bonding or being able to measure interaction kinetics
Mhm.
without significantly perturbing a biological system.
So writing a patent application is not that straightforward.
No, it isn't.
And this is your first one. So tell us about how did you decide you wanted to write a patent, and then how did you go about writing it?
Well, first we passed the idea behind what is now our new tech, the
Mm,
Office of Patent and Technology and Information Transfer. They screen these types of things and see if they think they're worth going into main patent. They do
mm,
some background searching for you.
mm.
Same thing was done back there. That actually wasn't my first idea for a patent. I had a couple back in the mid 90s, and they weren't quite as aggressive in getting patents back then.
Mm,
Probably should have patented some stuff, but they didn't.
yeah, yeah.
That was UNL's choice, not mine.
I should say Ruben Ricci said the same thing
Yeah.
about the mid 90s. They'd be rich if they had done this first
Yeah.
idea.
Yeah, he and I were this same, we were right across the hall from each other, so we had the same sentiments. Again, early 2000s, they started getting more aggressive, and that's when these started coming out.
That's true.
So yeah, there were unique applications. They were interested in getting anything they could as intellectual property in terms of patents. So they worked with us in terms of how to write up the patent. There's a very different format from patent and a research paper.
Yes.
You have to write down like what actually the invention entails, what are the main parts, what are the general parts, what's the data involved that you have, what are possible areas. And you want to try to make it as broad as you can to capture as much, but yet you got to be very specific in terms of what you actually did. So that was kind of a learning experience there.
Are there any other ones that we should talk about?
Uh, well, the ultra fast mu extraction one, that's the one I was talking about. We do a bit of work now with the microcolumns to be able to probe very, very short resonance times. That's actually made possible in the last 5 or 6 years a new class of analysis methods we call ultra fast affinity extraction, where we can study binding events between one agent and another. We probe that in a column that samples one of those compounds, like 100 milliseconds, just pull it out, get like a snapshot of the free and bound states of the things in the original sample. And then by changing the resonance times in our column, by changing flow rate, we can very precisely change the time allowed for the reaction. So basically with that approach, within an experiment that maybe takes seconds, you can get both equilibrium constant, rate constant information without immobilizing anything and without labeling anything. So it's very minimizing in terms of disturbing the system. I was looking for complex interactions.
And the one that seems out of place to me is this last one here, birefringence imaging chromatography based on highly ordered 3D nanostructure.
Yeah, that's actually
What is that about?
a clever project I did
Okay.
with Matthias Schubert over
Okay.
in
Okay.
electrical engineering.
Ellipsometry then.
He is Hewet, yeah.
Yeah.
And so we came up with a way where we could do thin layer chromatography on TLC plates, or maybe a centimeter by a centimeter.
Mm.
And on the supports, instead of having a silica support on there, which is normally done in TLC, there's actually grown nanostructures that use your TLC support.
Mm.
And those supports also act as a nice way of doing ellipsometry.
Mm.
So you're doing both a separation and a measurement on the same plate. So it was a combined effort.
Mm-hmm. No.
So he came up with the name of the patent.
All right. Let's talk about companies. Did you start any companies?
I've not started any companies. I've been asked, but I have not done that.
Sure. And then books. I know you've edited books, you've written books, textbooks.
Yep.
And I'm sure you've written plenty of chapters for books, but let's just talk about editorships and textbooks.
Okay. Well, a big one I have is the Handbook of Chromatography, and that came out in 2006, but it took me about 6 years to work on that.
Mm.
So I wrote about half the chapters in that text. It's about 30 chapters long. It's about 15 of the chapters. The rest are written by experts in the field from around the world. So I collected those, edited them. I did a lot of work in revision, went back and forth the authors a lot on those, and I can put them into a reference source. That's still, I think it's still regarded as like the leading reference source to fig chromatography. So it's still pretty popular, still sells a lot of issues on that.
Did you come up with a second edition?
Well, I may do that in the near future. This means it might be possible. Yeah, that's probably the next version, but it's been doing all right so far in its current version. And then, of course, textbooks. I have written several textbooks. I was the one of the authors on a one aimed at basically freshman chemistry for community colleges. That was John Kenkel and Paul Kelter. So we did that in the early 2000s. That was John Kenkel leading that and Paul Kelter dragging me into it. And then from that, we also got going on a textbook for analytical chemistry. So that one came out in 2010. I was the lead author in that one. Went through several possible co-authors, started out with Paul Kelter. Then Paul left here. So Jody was actually on there for a little while and he decided to bow out. So Jim Carr came on. So I was the lead author the whole time. I wrote about 2/3 of that book. Well, Jim Carr read the other third, and then I revised it, made it all fit together because we have different writing styles that make it uniform. So that came out, and that's been pretty successful also. Been translated into at least 4 languages, Italian, Portuguese, Mandarin, and there's one other one.
Yeah. Wow.
It's interesting to read them all. I can't read them. I can look at them.
You look at them. Okay. Which organizations funded your research and how did the funding organizations change since what it was in 1989?
I got my first bachelor grant funded in 1990. Yeah, so it's been the first one in 1989. Well, first was NIH. When I started here, all the new professors were applying for the R29, which is kind of like the mirror one, I guess now. It was a 5-year grant aimed at younger investigators. So I was able to get that my second round, which isn't too bad. So I had that. And that funded a lot of my early research. Actually, I had funding from NIH. I put 25 plus years from NIH in one way or another from that kind of stuff. And then later on, I also got funding from other sources like environmental stuff. I was able to get funding from the U.S. Geological Survey and the EPA, which isn't not funding quite so much fundamental research as they used to. They've changed over the years. And then more recently, we got more from NSF. They've kind of taken over the EPA. So more of environmental or fundamental stuff. Botanical methods has come from there. And also I've had industrial funding. I've used that. Those are usually smaller, but they're very and directed at specific projects. Like I have one right now I've been doing with Merck. It's a very specific project uh, looking at value affinity ligands. I did one I just finished with Zoetis, looking at new ways of measuring biopharmaceuticals using new affinity-based protocols. We had a couple nice papers out of that. So I've used various sources. Um, Most of it government funding, but some industrial funding too to kind of fill in.
Um, let's see. What techniques, you've mentioned them before, and instruments do you use, but give us a thumbnail sketch of high pressure liquid chromatography and whatever else you use.
Well, yeah, basically I'm an expert in chemical separation methods, so high performance liquid chromatography is the main one of those. That is a liquid phase separation method where you have a supporting material, like a particulate support silica particles. You place a stationary phase on it. It could be an absorbed layer or a bonded layer. In our case, it's a mobilized biological agent. You place it into a tube or a column. Uh, you pass through a mold phase where a liquid that contains your sample. Different components in your sample interact with the stationary phase, and the degree to which they interact changes the rate of travel through the system. So that's essentially what it is. It's a separation method based on rates of travel. But what we do is let's use a biological agent. We can use that to control the degree of separation. The selectivity, we can also then use it as a way to probe the rates and equivalent constant interactions and use that for isolation and all kinds of other things. We also have done a lot of capillary. So that's a method based on separation in electrical fields. So things with different charges, I migrate to the electrodes the opposite charge, also the presence of something called electroosmosis, moving along with the molar phase. So we can do that. More recently, we have also done work with field flow fractionation. We have some new equipment we got 3 years ago for that.
Wow.
Martha has.
I don't think I've heard about that.
That's a field separation method also. There you have a flow stream with a non-uniform flow profile, usually parabolic. You apply an external force to it. In this case, for our system that we have downstairs, we have a secondary flow stream, so push things against the wall. So you different rates of travel based on how things are getting to the different flow profile and how they interact with the field stream. So it's a way of separating, like size exclusion chromatography, but it does even larger ranges. You can get into things you can almost see with your eye and
So
separate.
good for mixtures then.
Yeah, it's good for mixtures. We got it from NSF for separating everything from proteins up to nanoparticles or polymers.
Really?
So it can do a pretty broad range of things.
Wow.
So we're doing some of that also now.
Wow.
So because I'm not just limited to HPLC, but that's mainly what we do.
Sure. How about detection? What are the different methods you've used?
Well,
Or what's your go-to?
our go-to is usually absorbance or fluorescence because it's easiest. But after that, then probably mass spectrometry. If we do without mass spectrometry, that works fine. It's just simpler, but we go mass spectrometry next, and then we can also do like chemiluminescence, near-infrared fluorescence. We've done electrochemical detection. We've done refractive index. We've done conductivity. So we did post-com reactions. So we've done lots of different things, but usually absorbance or fluorescence is the first round. If that's the easiest thing, then we'd probably try that.
So probably the hardest thing to detect would be something that does not absorb light very strongly.
Yeah,
that's your problem.
Yeah, that's where you probably would use mass spec, or you might use vapor light scattering or something like that.
Yeah. In some ways, science is cooperative and competitive. So I'd like to know if your work was ever scooped, or did someone produce similar results at the same time?
I wouldn't say scooped, but I did have a couple times. So this is actually, I was an assistant professor, and we had another person, a famous person in my area who you know, Fred Vernier, visiting our department. And he and I actually have worked in many similar areas over the years. So we know each other pretty well. And we're good colleagues. So he was there visiting, and I was giving a tour. We talked about the types of stuff we were doing. And we realized in talking to each other that we were working on a very similar project without trying to give away to each other some of the details. I kind of left there thinking,
I better work, get this out.
So anyway, we were both pretty close. And it was actually a new method of doing immunoassays by chromatography based on what's now called a sequential injection format, competitive bonding sequential assay. So you have an antibody, it's in a small amount of column, you inject a sample through there. It captures the things from your sample you want to bind the antibody. And then you inject a probe after that, so it's sequential, and you see how much that binds. So it's different than normal competitive binding assay because it's not all can be at the same time. But it has a lot of advantages to it because you're not actually applying your sample and your label at the same time. So you can change a lot more things on it. And it's pretty fast to automate. So we came up with both our papers appeared, I think, within back-to-back issues of the same journal, Medical Chemistry. And it turns out that we use almost exactly the same model system.
Oh, wow.
We both use antibody columns against albumin and albumin as analyte. And the reason for that is that 5 years earlier, as a graduate student, I published a paper looking at albumin binding antibodies against albumin and worked out there's some very well-defined elution and mold phase application conditions. So everyone has started using it as a model then. So he had actually picked my model for that reason, I think. Okay.
So you inspired his project.
I inspired his project in some way. But anyway, even though our papers came out almost back to back, we dealt with slightly different things. He was dealing with more practical issues, and I had basically come up with the theory, a model to describe how the whole thing worked.
Oh, yeah.
So they were complementary. So that's the closest I would say to scooping, but I'd say it was probably more simultaneous publication.
Who was the grad student on that?
That was Dave Thomas. He was one of my first students.
Okay, yeah. And so he was doing the math.
I was doing the math.
You were doing the math.
He was doing the experiments.
Okay. I remember that.
Yeah.
Let's see. And were your published research ever contradicted, and how is it resolved?
Not contradicted. There was one case, this is probably 15 years ago, where one of my students came up with a new method that we wanted to try for measuring like drug competition on a protein column. And I remember when we had it come out, I was thinking, okay, there's something bothering me about this method. It looks like it works on paper. We tried it, looked like it worked. And we got it published. I got an email from someone else in my area that's pretty well known saying, well, I got some concerns about this, some assumptions made here. And so I really appreciate they contacted me about it.
Yeah.
So we talked to each other.
That's nice.
I said, how about this? How about we redo the experiments in a different format just to check it? And I'll include you as a co-author since you pointed this out to me, and we can include your concerns and see if we address them or not.
Awesome.
And so we did that. And it turned out we were fine. Yes, they had the correct concerns, but it turned out it didn't matter with how we're doing it. So we were both satisfied. They got to express their concerns. We got to show, yes, this is what you got to think about when you're doing this. So it actually came out a stronger paper as a result. So I was glad how that turned out in the long run. It could have been worse.
No, that is pretty good. Have you ever published a correction?
I've had small, what they call correndums, yeah. There's been a couple where like the journal, like in the galley proof process, didn't catch one of our corrections. They had something small wrong on the figure, so we had to correct that. There's one case where one of my students accidentally put in the wrong units for like a concentration on an important reagent, so we had to have some correction on that. But so far, that's been it.
So just editing kind of stuff.
Editing type stuff. So I've been fortunate that way. I do try to be pretty hard on my own papers before they go out, but there's just so many things that can go wrong with papers. It's impossible to kick everything.
Totally. Is there anything else you want to say about your research before we move on to other career activities?
I would say that it has taken some unexpected turns over the years.
Okay.
Like when I first came here, I was interested in doing clinical applications, biomedical applications. And within 4 or 5 years, I was doing environmental stuff. That is partly because where I was, I had to fit into with my environment.
Sure.
There was another case, this is probably 10, 15, 12 years ago, where I was doing work with the company. We are starting to look at brain injury markers. And we had not even started the project. We just gotten the funding, and all of a sudden UNL decided they want to advertise this. And all of a sudden there's all these news reports coming out how we're having to develop scanners for looking at brain injury. I got an interview on an ESPN show to talk about brain injury trauma. Wow. I thought, okay, I didn't expect my research was going to go to that direction. So that was actually kind of fun, but yeah,
Yeah.
it was
Wow.
unexpected.
That is unexpected.
Never thought I'd be on ESPN my entire life.
Okay, great. Other career activities, right? So we've got complicated lives as professors and we're interacting with each other.
Mhm.
Tell me about societies that you belong to, conferences you regularly attend, and is there a meeting that was especially memorable to you?
Mm. Okay, well, in terms of societies, I mean, I'm a member of the American Chemical Society. I'm also a member of the American Association for Clinical Chemistry. I've been in my entire career for that. Um, about Physical Society, I remember that. There's some other smaller ones, but those are probably the main ones. Oh, of course, AACAS too, American Association of Science.
Mm.
Um, in terms of conferences, I usually go to the HPLC conference series. It's in the United States every other year. So when it's in the US, as an editor, I've been able to go to it overseas too because
Mm.
the editorial beings, they pay for my travel.
Mm-hmm.
Can't normally do that through US grants.
Yeah.
I do enjoy going to the affinity conferences there every other year, but they kind of circulate around the world. I'd say probably some of the most memorable ones have been those. When I was an assistant professor, I actually got invited on a special travel grant to go to one in Kyoto, Japan. That was fun. That's my first experience with jet lag. That's a big jet lag.
That is a big one. Yeah.
And then also that same conference in 2017, I won the Affinity Chromatography Award.
Oh, wow.
That's a big one.
Mhm.
And so
That would be memorable.
that was in Paris, France. So that was a very nice conference. I
Yeah.
got to take some of my family along. And actually, I can show you after this talk here, one of my prizes of my award for that
Mm.
was it gave me a nanofabricated Eiffel Tower. So it's
Oh,
about 1 kilometer tall. It's in my
oh, cool.
office.
I want to see this.
You can see it under a microscope. You actually look at the eye, you can see the Eiffel Tower there. That was part of my award. So that was pretty cool.
That's cool.
Yeah.
Did you ever take any sabbaticals and did it change your research direction?
Yeah, I've had a couple sabbaticals. My first one was after I became a full professor,
Mm.
and that I spent to work on my textbook.
Oh, okay.
So that was the first one. The second one I had, it's probably 10 years after that. And it turned out I was going to work on some research in textbook, but it turned out that's also when our chair asked me to work on a Cobra grant.
Oh.
So I had an effort for that.
Mm.
That grant, although we did not get it at that time, it eventually evolved into our SIPSI grant today. So we took a lot of components of that and they were adapted into the one we have. So I guess
Mm.
it was productive in that sense. It did lead further on down the road.
And SIPSI is for?
Well, the NSIPC is the full name, Nebraska Center for Integrative Biomolecular Communications.
There you go.
Yes.
That sounds like it's right up your alley.
Yeah.
Service contributions. So we have lots of meetings all the time, everywhere, in the department, the university, the community, nationally. Tell me what you remember most.
Well, I was the chair of the graduate committee for a while. That was a fair amount of work, and that was very memorable. Helping graduate students. I've also been members of the executive committee for several major things on campus. I was one of the starting members and then still current member of the MMOD, the Molecular Mechanisms of Disease Fellowship program, which is run through biochemistry but involves many departments. So I help out with that. We had a center for toxicology for a while between here and UNMC. I was some executive committee for that. So those are kind of memorable things, I think.
Yeah. Real fun. What courses did you teach or do you teach more often than others? And what are your thoughts about those courses?
Well, the one I taught probably the most is Chemistry 824. That's our analytical survey class, which I created that course. So when we first started here, our department decided they were going to go to a new system where they had a couple of core courses they wanted all of our students to take. And that was the one that the analytical division decided to develop. And it decided, since I was the new person on the block, that I'd be the person to develop it.
You get your finger on the pulse.
Yes, I was there day one. So I've been working on that over the years. That's turned out to be a pretty successful course, I think.
Oh, yeah.
Probably half the students in our department have taken that.
Yep.
And then also I teach our chromatography course, 825G. I've done that for many years. That's still been changing and been pretty successful. Probably another one that's really gotten a lot of attention is my data handling statistics course, 825E. So that started out actually at the request of our department also. It used to be a course taught by Marjorie Langell, a physical chemist from our department, and it had been set aside for many years, and they decided no, somebody to teach it. It was a 1 credit course, and it was a lot of work for 1 credit.
Yeah.
We changed it to 2 credits 5 or 6 years ago. It's still a lot of work for 2 credits, but it's been pretty popular with students trying to make that something they can use across different disciplines.
So tell me about then 824, the analytical chemistry. Started that a long time ago. How has it changed over time?
Well, it's designed so it can change. That's one good thing about it. It's designed so that we talk about the main areas of analytical chemistry. We do a quick survey, and it's designed so that students are placed, they hear from people that are experts in the field. So, for example, and I teach probably half to 2/3 of the lectures, depending on what year it is. But the other lectures are given by people that are experts in the field. So, for mass spectrometry, for example, when I first came here, Mike Crosse taught the section of mass spectrometry.
Beautiful.
But then he left, and then
Right.
David Smith took over that section of mass spectrometry. And then he left.
Yeah.
And then Ron Cerny did it for a while, and then Eric Dodds, and then now Jared Shaw.
Oh,
And every one of them has had a different way of teaching it.
sure. I bet they did.
I've got to see everyone's point of view on mass spectrometry over the years. And as a result, I can give up, and I can give it a lectures of mass spectrometry very easily. I've got all their notes too from those years. So I've seen everything from simple gas phase reactions up to the current emphasis on protein structures analysis. So that's happened in all the years. So the same thing with NMR. I've seen many people speak about NMR over the years, starting with Tom Apple and the Rich Shoemaker and so on and so forth. So it's been an interesting class from that point. Actually, the challenging thing about that class is keeping everybody organized
Sure.
and also making sure everything is at an appropriate level. So I maintain full control over the problem sets and the exams to keep everything even. But then I have the lectures are asking by experts in the fields where I can. If they're not, then I do it, and hopefully I can handle it. Again, I've given lectures in everything in that class, so
Sure.
sometimes I have to do it. I come down there and someone forgets to show up, and I give a lecture on the topic. And that happened more than once.
Oh, again, it's been a long time since that course was started, so I'm sure a lot has happened.
Yeah.
All right, let's move on to youth. Where did you grow up, and what was your childhood like?
Well, I grew up in rural Wisconsin on the west side, near the Mississippi, but actually in the hill area just east of there. So I actually grew up on a small farm. I'd say it's probably more hobby farm. My family had land that area since like the late 1870s. So I actually grew up on my great uncle's farm, small dairy farm, and so very rural setting. Since it's very hilly, I can tell this to my children truthfully. We had our driveway went down one hill up. Sometimes the winter we had to walk out to the mailbox. I actually did have to walk uphill and down to school every day. I really did have to do that in the wintertime. So it was about a mile walk out there too.
So, did you have other childhood friends? I mean, how did you get together if you were on a farm?
Yeah, we walk and you bike and stuff like
Yeah.
that. So it's a couple miles away. We hike around a lot.
Yeah. All right. When did you develop your interest in science or math?
Oh, that's pretty early on. I remember, well, grew up in the country. I spent a lot of time out in the woods and in the fields and stuff, and I paid a lot of attention to nature. Um, I don't have my own little pseudo chemistry thing in the basement. I play around with reactions and stuff.
Oh, wow.
Nothing too complicated, just burning things
Yeah.
and combining this together.
The
Yeah.
lava reaction.
Yeah, yes. And then my grandfather, he actually had a fishing lure business. He tied his own fishing lure. He had a place not too far away. We had a trout stream, so I go out there quite often and play in the fields and stuff and get a lot observing of nature that way too. So I was actually more interested in biology when I was in high school. And then so that was pretty early on. And then I was always doing sciencey type stuff. Everyone thought it was really weird.
So lacrosse, then your major was what?
Chemistry and biology,
Chemistry,
double
biology.
major.
Okay, there you go.
Yeah.
And then you chose Iowa State.
Mhm.
And tell us how you chose Iowa State, and then what did you do there?
Well, when I was at lacrosse, one of my teachers, my physical chemistry teacher, was actually from Ohio State. She was always promoting it. So I know it had a good reputation, and it was in a drivable distance, being able to go home once in a while. So I just had a lot of attractive
It's
features
about
to it.
what,
Yeah,
300 miles or something, or
it's 250.
250.
Yeah, and then so moved there. There was actually a professor there that was starting to work in combining biological agents with analytical chemistry. Back then, the term bioanalytical wasn't really around
Oh,
yet.
really?
There weren't many people doing any kind of biological stuff.
Wow.
You're either biochemist or you're an analytical chemist, but you weren't
Right.
anything in the middle.
Cheapers.
So I was trying to go for the middle ground. So, and then their biochemistry department was actually the same building as the chemistry department, so that was also nice too. So a lot of things like that kind of attracted me to it.
So what was that? What was your thesis?
Well, I actually had, as an undergraduate, I had a thesis in both biology and chemistry. So I had two undergraduate theses. And in my graduate work, I had a PhD in analytical chemistry, and my thesis was on the split peak effect in chromatography, that was kind of a happy accident for all that thing. So there's a story there too. My very first couple of weeks of graduate school, I started working for my professor, and he had me working with the more senior student who's being very frustrated working their project. They're working with something called protein A, which is, of course, very popular now as a bonding agent, but we're trying to figure out how to put it into a column for the first time. No one had done it yet. And he got it kind of there, but wasn't working very well. And it also wasn't binding to things very well. And so I said, okay, let's give it to the new guy and see what he can do with it. So they trained it, and I looked at it, and I did a couple experiments, and this doesn't make any sense at all how things are going. So I was walking home one day because it's like a mile walk to my apartment from campus. It occurred to me that one thing that's probably the issue is it looked like the protein just wasn't getting into the pores of the support we're trying to make. So I was thinking, okay, why couldn't that be? And I realized, well, maybe there's air bubbles in there.
Oh,
Okay, so and they weren't really doing anything with that. So I went back lab the next day. I tried again, and I took the support. I placed it into ultrasonic heating bath for a long time to shake all the air bubbles out, and it worked great. So I actually figured it out, and all of a sudden everything started working. The other student took that on; they could work with it.
Oh, wow.
And then we found out also that the other part where things weren't bonding well is it wasn't that the thing he was injecting was inactive or we're overloading it. There's something else going on. He couldn't figure it out. So I started doing the same experiment with the columns I just made up. And all I did different was I went to a much lower flow rate than he did just to make sure I could bond it all. And all of a sudden I saw a big increase in bonding. And all of a sudden our advisor got all excited because he just had this theory that he talked to some other mathematician about something called a split peak effect, something predicted in chromatography decades before no one actually seen. And it turns out that if you have something that's large enough bind to something slow enough, you could in theory see it, and I just saw it.
Oh.
So that resulted in actually my first paper, and the other student was pretty frustrated. They didn't slow down the flow rate. Anyway, so I got a paper. I got the feature paper in analytical chemistry out of that, the very first one.
Wow.
Yeah. So that was pretty exciting. That was all because I was bothered by something that I couldn't get to work.
So when we're talking slow flow rate, we're talking what? 0.1 mil a minute?
I actually went down to 0.01.
Oh, wow. That is slow. Nobody would really do that, would they?
Except I did. I was crazy enough to try it. I was crazy enough to try that.
Okay, so you're done at Iowa State, or you're finishing up at Iowa State, and you're choosing a postdoc. And so, how did you do that?
Okay, so I had as an analytical chemist the tools I wanted to learn to use and I had to use. I wanted to look for applications, so I wanted to make an impact. And I figured clinical chemistry might be a good area to go into. So I kind of chose a non-traditional route for my postdoc. I knew that the Mayo Clinic had actually a postdoc program in clinical chemistry and laboratory medicine. They took applicants for a broad areas, so you didn't have to be a biochemist, you didn't have to be a pharmaceutical chemist. So I applied and I got in there. And so basically, it was a program where the first year you rotated through all the different laboratories in the clinical laboratory medicine. So I actually had a whole series of advisors. Technically, I was in medical school at Mayo Clinic for 2 years.
Oh, really?
I was actually part of, yeah.
I didn't
I
know
was
that.
working with the residents and pathologists back to back. So we're all trained together. And then the second year is when I picked one of those pathologists as my postdoc advisor. Then I worked intensely on a project for research. So it was a little bit different setup.
Yeah.
But I learned a lot. I basically had a crash course in medicine
Yeah.
through all that.
And do they still do that program?
They do.
Okay.
Today, I would say it's probably more focused on people that want to be directors of clinical laboratories than it was back then, but they still have it kind of set up the same way.
And were you novel in having a chemistry degree?
There was one other, they took a few others that were in there. But yeah, I would say probably a third of the people had chemistry degrees. Others are pharmacologists and some are biochemists. It's kind of a mixture.
Let's see. We are coming toward the end here. What research and writing did you do to merit your authorship of your first paper? You already said
I
that.
did, yeah.
Yep. You already told us about that.
I was very lucky.
Yeah. So then, in retrospect, how far did your research as a professor diverge from your graduate and postdoctoral work?
Well, I'm still using HPLC,
Yeah.
so that's the same, but I've changed lots of things that I do with it. In terms of the clinical stuff, I've used a lot of the ideas I got there. I mean, when I was in my postdoc, I was actually working with peptide hormones, which is actually kind of ironic. Some people in our Department of Research on peptide hormones
Absolutely,
right now. Yeah. So I was doing measurements of like parathyroid, the peptide hormone, and also insulin a little bit and some other things like that. So rather than focusing on actually the analytes, I've been focusing more on the applications, developing new technologies, looking at fields. And obviously, I already mentioned about not just clinical chemistry. I've been going a lot into biotech and environmental stuff and forensic and materials chemistry, all kinds of different things I didn't do back then.
A lot of collaborations, right?
Yeah, a lot of collaborations.
Okay, now on to the personal section. Tell us about your family. I know you married and I know you have kids. What do you want to say about that? And how'd they fit into this story? When did you get married and where did you have kids?
Well, I met my wife, Jill, when I was in college.
Okay.
We both went to, for a while, the same place, La Crosse, and she went to Madison for a couple of years after that. So we had kind of a long distance relationship for a while. Got married right after college. So she went with me to graduate school. We were married actually 2 weeks before I started graduate school. And so that was kind of our honeymoon, we say sometimes.
Poor Jill.
Stay at first. So she's been very supportive for me all the years. And actually, at that time, she was working at Iowa State. She made a lot more money than I did.
Back then, grad students didn't get much money.
No, we didn't get much money. And then I have 3 kids. We had 3 kids together. Our first one, Ben, was actually born when I was in graduate school.
Okay.
Our second one was born when I was a postdoc. Actually, he was born just after I did my interview here.
No.
This was the last interview I was going to take because I didn't want too close to the due date. So, and so he was like 6 months old when I actually moved here. And then, of course, our daughter, she was born after I was here for a while. So, and they're all in the area. They're all doing well. One's married, one's engaged, and the other one's a postdoc at part of startup companies.
Oh, wow. Okay. So, what do you do with your free time, your relaxation and
I
entertainment?
don't have much free time. Well, okay,
A foreign concept.
my wife Jill teases me, says I basically do for my fun the same thing I do for work. I tend to organize stuff. So, as you know, I do a lot of work with family history when I have a chance, genealogy. I've been doing that for many, many decades. Right now I'm collecting old pictures, so that's kind of fun. They got my prize picture. I told you just about this before, I think. I got a picture, actually, a daguerreotype of when my family, the Hages, came over in the 1870s. They got off the train at final destination. They met the people to pick them up there, and they got these topics. I took a daguerreotype of that.
Wow.
So they got here. Yeah, and I got that picture.
Wow. That's amazing.
Yeah, so that's pretty cool. So I've got a lot of stuff passed to me through my grandparents. So I like that kind of stuff. I also do, a lot of collecting of things, coins and shells and stuff like I've been doing for years and years. Yeah, and I always get teased by that by my wife.
I'm a collector too.
And also, and I like to still go out hiking. I take my son and I go bird watching quite a bit on weekends. He's more intense in it than I am. I just like to get out in nature and
Yeah.
camping, hiking, that kind of stuff, and fishing sometimes. But
What got you interested in family history?
well, actually, my grandfather was doing some of that way back. He did actually a family history back in the 50s.
Mm.
And then when I was a young lad, I saw this book he put together. I said, hey, I kind of like to improve on that. So I took what he did and I developed it. And
Mm.
I've been going kind of really far back. I
Mm.
know. Now, coming where I do come from, Scandinavia, you can go quite far back.
Yeah.
Almost all my sides, I can go back at least to the 1400s, some
Yeah.
even further back than that.
Great records.
Yeah, yeah. The Norwegians and Swedes really know how to take care of records.
So yeah, how about last names? Is it constant through
Hage,
time in Norwegian
well,
documents?
well, there's lots of different names. That's the one that my ancestors took when they came over here. It's
Oh,
actually
okay.
a farm name.
Okay.
Hage, actually in Scandinavia, it's Hage.
Okay. Yeah.
So I'll answer to either one if I'm in Europe. And actually, it's the same kind of word, actually, in Dutch. It turns out Hage means like garden.
Oh, okay.
Excuse me. It's actually the same where the hedge comes from. Hedge and hage,
Oh,
like a garden area, sort of. Yeah.
yeah.
So yeah, it's a farm name. I actually know where the farm is in Norway too. And there's actually a whole series. And it's in the central area, Gudbrandsdal, that they're all from.
Mm.
At least on my side.
And have you been there?
I have not been there.
Oh,
I have
wow.
lots of pictures and all kinds of satellite photos. Probably one of these days soon I will get
You
it.
know where the farm was
I
located.
know exactly where it's. I have the coordinates. I know who lives there.
All right. Well, thank you very much for talking to me today. I've enjoyed hearing your stories.
Okay, thank you.